Welcome everybody. Today's webinar will be about performing fatigue analysis for cyclically loaded static equipment. Our agenda today would begin with an introduction to AutoPIPE Vessel, then brief discussion on fatigue analysis and why it is important. We will talk a little bit about the Rainflow method of cycle counting, followed by a detailed overview of the user interface and fatigue calculations and report review. Finally, we will wrap up by taking a look at what all global fatigue codes are offered in the program. AutoPIPE Vessel powered by Microprotol is a software that can design virtually any type of pressure vessel, air cooler, heat exchanger, and tanks to most of the major global design codes. One of the strengths is the ability to import thermal design data from HTRI, Aspen, ProSim, and Honeywell, as well as exporting to the major CAD software and plant design software like PDS and AutoCAD SolidWorks MicroStation. The software is ideal for both EPC companies as well as equipment design and fabrication companies. There are several advantages of the software, including maximizing productivity of skilled engineering resources, supporting a global market, and improved collaboration across distributed project teams. AutoPIPE Vessel offers a wide range of global vessel codes, including regional wind and seismic, global design codes which are French, American, British, German, Russian, European, and the recently introduced Chinese GB150 code. It also supports local analysis methods and comprehensive regional seismic and wind loadings for Canada, India, ASE, European, Russian GOST, British, Brazilian, Spanish, and Chinese. There are several users worldwide, including major EPCs like Jacobs, Technip, and Saipem, nuclear EPCs like Areva and Babcock & Wilcox, inspection authorities like Lloyds, SGS, and Bureau Veritas, as well as oil and gas companies like Petrobras and ExxonMobil. AutoPIPE Vessel has powerful CAD export feature generating 2D drawings and 3D models for MicroStation, AutoCAD, and SolidWorks. Shown are some examples of 3D SolidWorks model created automatically from a designed exchanger using the interface feature. So let's begin our topic today. Fatigue is defined as weakening of a material caused by repeatedly applied loads. ASTM defines fatigue life NF as the number of stress cycles of a specified character that a specimen sustains before failure of a specified nature occurs. An important method for fatigue analysis is using an SN curve as shown above. It measures and plots the number of cycles to failure due to application of a cyclic load. As we see, if the stress amplitude is decreased, the fatigue life cycle increases on a log scale. Shown is a typical brittle aluminum SN curve. A pressure vessel can be subject to several types of cyclical time-varying loads. In the pressure vessel, the welds are more prone to fatigue damage than the base metal. This is due to the fact that the welding process heavily affects the microstructure properties of the weldment, which may be more prone to crack initiation due to cyclic load. The stress amplitudes that a pressurized equipment undergoes can be modest in amplitude if considered as mere static load, but may initiate microscopic cracks in the weld joints due to prolonged operation, and eventually the crack propagation may lead to fatigue failure like shown in the picture above. In the case of simple periodic loading with constant tension compression stress amplitudes, an SN curve may be sufficient like shown in the top image. But how to perform fatigue analysis if the stress amplitudes are not uniform and are applied as a load spectrum consisting of varying amplitudes like shown in the bottom image? For this, a cycle counting method like Rainflow method is essential. The Rainflow method is used to determine the time points representing the individual cycles for the case of situations where the variations in time of loading, stress, or strain can be represented by a single parameter. It essentially reduces the spectrum of varying stress into a set of simple stress reversals. This method is applicable only for proportional loading, and the cycles counted correspond to closed stress-strain hysteresis loops, with each loop representing a cycle. Like discussed above, the Rainflow algorithm is a process to obtain equivalent constant amplitude cycles. The method was developed by Matsuishi and Endo. Now let's look quickly at the Rainflow algorithm. Imagine you have a loading spectrum as in the figure shown above. The Rainflow algorithm works something like the following. First, reduce the time history to a sequence of tensile peaks and compressive valleys. The time history is rotated at 90° clockwise. Each tensile peak is imagined as a source of water that drips down a pagoda roof. Count the number of half cycles whenever the flow terminates, which occurs at any of the following cases. 1. It reaches the end of the time history. 2. It merges with a flow that started at an earlier tensile peak. Or 3. It flows when an opposite tensile peak has greater magnitude. Then repeat above steps for compressive valleys. Assign a magnitude to each half cycle equal to the stress difference between its start and termination. Pair up half cycles of identical magnitude but opposite sense to count the number of complete cycles. Typically, there are some residual half cycles. Now let's look at the user interface of the fatigue analysis module of AutoPIPE Vessel. In the first image, the design code is selected in the Design Parameters tab. The second image shows the fatigue application checkbox in Operating Conditions tab to enable fatigue calculations, and the last one shows the checkbox in the Report tab to show fatigue calculations in the report. Subsequently, the fatigue analysis is selected from the menu Insert, which opens the user interface for fatigue analysis. The load histogram can be easily applied. To the right is shown how a new load definition can be added, erased, moved by the vortex move, erase, or insert commands. The rainflow calculations are performed by clicking on the Apply Rainflow Method button. Let's look at the types of cycles defined for the above example. Type 1 defines a single cycle with a pressure range of 0.3 and max pressure is equal to 0.3 and mean pressure is equal to 0. The time scale is set as days and life duration is equal to 10 years. Hence, the total number of cycles in this lifespan would be 365 days a year times 10 years is equal to 3650 days. AvT is the assumed mean cycle temperature for cyclic loading. TAV is equal to 0.75 times Tmax plus 0.25 times Tmin. This is the most widely used formula for average temperatures in codes and is adopted in the program. Type 2 defines again a single cycle with a pressure range of 0.1 and max pressure is equal to 0.15 and mean pressure is equal to 0.05. This is as can be seen from the highlighted section in the load diagram, the max and mean pressure settings. Cycle type 3 likewise has only one occurrence with a range of 0.2. Finally, type 4 has maximum number of occurrence, total 6 occurrences in the whole cycle, with range of 0.1 and max and min pressure is equal to 0.3 and 0.2. In the default weld joint tab, the various weld types can be defined. From the drop-down, the weld types can also be changed or a different selection can be made as shown on the right image. The third tab in this module is for defining the weld map. The weld list can be viewed, which lists the numbered welds, and each weld type can be double-clicked to open the detailed definition dialog box as shown on the right. The weld joint type can be selected from the drop-down. As an example, the W5 weld for the shell barrel can be modified to joint type of from one side no backing. Individual weld detail tabs can be opened by double-clicking on the weld shown in the weld map. For example, the weld W41 description tab is displayed. Now let's take a look at a demo. I've already created a vessel, I've modeled it, I've specified the design codes, ASME Section 8 Division 2, I've checked that, I've set the design conditions, in the operating conditions I've checked fatigue apply, and the report I've checked fatigue analysis, so that the report displays the fatigue report, fatigue analysis report. I click on Insert, then Fatigue Analysis. Load histogram is already specified. I can click on an individual data point and I can either change the data, I can click, right click and then move very conveniently. I can erase vortex, I can right click and insert vortex. Then when you apply Rainflow method, it computes automatically. The default weld joint tab, all the butt weld, shell and head, butt welded cone without knuckle radius, intermediate head, double jacket, etc. All these weld configurations can be defined. So you can say butt welded shell and head, you can select angle more than 150, less than equals to 150, from one side no backing, visual examination, butt welded ground flush, butt welded cone without knuckle radius, you have smooth finish both sides, angle more than 150, less than equals 150, intermediate head, double fillet weld, button fillet external pressure, button fillet internal pressure fillet weld, double jacket sealer closure welded both sides, welded one side, visual inspection, welded one side, no root inspection, butt welded flange, nozzle and boss, butt welded nozzle, shell side. So as you see, different types of weld geometries can be specified for each type of weld. Moving on to the weld map. Like mentioned earlier, there's a weld joint list, and it lists all the weld tags and the component designation with the tag numbers. You can select individual weld tag, double click, and it brings up the joint type. Here also you can specify individual joint type. You can set neutral fiber offset, local circularity deviation, angle from long elliptical section axis. Field in the nozzle welds, set on two sides welded, set on legs finished, set on one side welded, etc. You can double click on individual welds in the weld map and bring up the weld map details, the weld details for that particular weld. Okay, so I'll calculate now, perform strength calculations. Calculation is completed. Let's review the report. This is the design report. It is easily navigable. On the left hand side, using the navigation option, go to fatigue analysis. The first part of the report for fatigue analysis lists all the elementary cycles grouped by type. So all the three cycle types 1, 2, 3 are listed with the corresponding number of cycles, the maximum minimum pressure, the pressure range, and the T-mean, the mean temperature. Then it lists all the weld tags and the assembly type, followed by a detailed formula section, and then individual tags, weld tags, are reported for the fatigue calculations. Finally, for the particular weld type, accumulated fatigue damage is checked whether it is less than equals to 1 or not. So in this particular case, we see for tag W1, it passes the fatigue assessment test. Likewise for W2, it performs same calculations. Since now we have an overview of the user interface and having seen a demo, let's review the calculation details and the relevant report sections. For this example, we will consider the fatigue analysis performed according to ASME Section 8, Division 2. The fatigue analysis for Division 2 is based on Part 5 and Annexure 3F, which provides design curves and equations for obtaining permissible number of cycles. The first step in fatigue analysis following Division 2 is the fatigue screening step performed according to Section 5.5.2. Basically, the need for performing a detailed fatigue analysis is first assessed by performing the screening step. There are two methods in the codes, A and B. Method B is used in the program. Detailed fatigue analysis is necessary when the screening fails or the specified number of cycles is more than 1 million, for which the above screening criteria is no longer applicable. The distinct fatigue cycles obtained by applying the Rainflow method to the load histogram is listed in the beginning of the report, as shown to the right as a table. This table is most important since it provides the most critical data for the fatigue analysis and would be frequently referred in this presentation. In fatigue analysis, each individual weld is analyzed separately for fatigue. In our example, we will consider only the weld tag W1. The step 1 of the screening process is determining the fatigue screening factors C1 and C2. These factors are obtained from the table 5.10. The value is mentioned in the report table as highlighted. Step 2 involves determining the stress amplitude, which is obtained by multiplying the screening factor with the allowable stress S to obtain C1S. C1S for the first cycle K is equal to 1 is thus obtained as 453 megapascal. In step 3, first the stress amplitude SA is used to obtain the stress factor Y, which is 66.57 for the case of cycle 1. The value of elastic modulus EFC is provided in the table. The exponent X is calculated from the value of Y and a curve fitting process for which the 11 polynomials are listed in table 3-F.1. Finally, the value of design number of cycles N is obtained as 10 to the power of X and is equal to 1819.7 as stated in the report. The pass criteria for step 3 is that N delta Fp, which is the actual number of cycles, must be less than the design or permissible number of cycles N obtained above. In our case, we see that this criteria has failed since the actual number of cycles, 3650, has exceeded the obtained design value of number of cycles, that is 1819. Step 4 includes comparison of maximum range of pressure fluctuation delta Pn, which is 0.3 megapascal for cycle k is equal to 1. The value should be less than the parameter of P by C1 times SA by S shown above. As we can see from our report, both the criteria in the previous steps have failed. The actual number of cycles exceeds permissible design value and also the maximum range of pressure fluctuation exceeds. If any of the above conditions fail, the screening fails, and in this case both the conditions are not satisfied. Hence a detailed fatigue analysis is necessary. So let's review the fatigue analysis process. There are 3 methods stated in division 2. The first method is 5.5.3, fatigue assessment following elastic stress analysis and equivalent stress. Method 2 is based on 5.5.4, fatigue assessment using elastic plastic stress analysis and equivalent strains. Method 3, which is 5.5.5, fatigue assessment of welds, elastic analysis and structural stress, is the only method used in AutoPIPE Vessel. This method is recommended for welded joints which are not machined to a smooth profile. Welded joints with controlled smooth profile should instead use 5.5.3 or 5.5.4. The method 3 following section 5.5.5 is to evaluate protection against failure due to cyclic loading using the equivalent structural stress range. The actual detailed fatigue analysis in this method is very involved and comprehensive and beyond the scope of this webinar. Hence, we would look at the brief overview and understand the process of the fatigue evaluation. This method essentially involves a hypothetical crack plane assumption. The method starts with step 1. Step 1 is used to determine load history based on user specification. Step 2 is used to determine individual stress-strain cycles by the Rainflow method. These 2 steps have already been explained before. In step 3, first the elastically calculated membrane and bending stresses normal to assumed hypothetical crack plane at the start and end points, which are time points mt and nt respectively for the kth cycle counted, are determined. Notice these are the values in the report to the top right corner. For example, m sigma emk denotes the membrane stress at the kth cycle for the time point m for the cycle. E means elastically obtained. Likewise, m sigma ebk denotes the bending stress at the kth cycle for the time point m for the cycle. Using this data, calculate the membrane and bending stress ranges between time points mt and nt in the maximum, minimum and mean stresses as shown above. In step 4, the elastically calculated structural stress range for the kth cycle is determined. This is the parameter delta sigma E with suffix k for the kth cycle. In step 5, the elastically calculated structural strain from the elastically calculated structural stress obtained above is determined, where EYAK is the elastic modulus at the mean temperature at the kth cycle. Subsequently, Newber's rule is applied to solve the equations above to obtain the local nonlinear structural stress and strain ranges delta sigma k and delta epsilon k. Further, the stress range is modified for low cycle fatigue. The values of the local nonlinear structural stress and strain ranges are highlighted in the report. In step 6, equivalent structural stress range parameter for kth cycle, which is denoted as delta S ESS, is obtained. The terms for this parameter calculation come from the local nonlinear structural stress range delta sigma k and few other parameters that are calculated based on the various stress strain parameters from step 3. The next step, step 7, is used to determine the permissible number of cycles nk based on the structural stress range parameter for the kth cycle, which is delta SESS, computed in step 6 above. Step 8 involves determination of the fatigue damage DFK for the kth cycle, which is the ratio of the actual number of cycles to the permissible number of cycles calculated in step 7. Finally, in steps 9 and 10, repeat the steps 6 through 8 and compute the accumulated fatigue damage for all the cycles. The summation of the fatigue damage, which gives the accumulated fatigue damage, must be less than equals to 1 for the fatigue assessment to pass. This is the parameter dF shown above, which should fulfill the criteria of being less than equals to 1. Shown above in the report, the delta SESSK are computed for all the k cycles as in step 6, and the following permissible number of cycles n computed for the corresponding kth cycle as in step 7. Then the fatigue damage factor obtained by dividing the actual to the permissible number of cycles, which turns out to be 8.13 times 10 to the power minus 5 for k is equal to 1. Likewise, all the fatigue damage factors for all the cycles are summed up to obtain the accumulated fatigue damage for that joint, which is less than 1, so the joint passes the fatigue assessment. This fatigue analysis is performed for all the weld joints for the complete fatigue evaluation of the equipment. Shown above, the report clearly states all the formulae, which is very conveniently referenced by the engineer, and it helps in reviewing or checking the calculation results. Now let's take a look at fatigue analysis for all the global codes which are offered by the program. Let's start with CODAP. The screenshot above shows the typical fatigue evaluation for CODAP Division 2 C11.2. Eurocode EN 13445. Notice that the ratio of actual by permissible cycles is displayed, similar to ASME Division 2 report. AD Morgblatter German code. Observe that where the ratio of actual by design cycles exceed 1, it is highlighted in red to draw users' attention so that corrective action is taken. British PD 5500 code. And finally, Ghost Russian code, which uses similar criteria of ratio less than 1. Thank you for attending today's webinar.